Welcome back, everyone, to our ongoing deep dive into the world of the OEIS.
The Online Encyclopedia of Integer Sequences?
Or OEIS for short.
Yeah.
As always, for those just joining us.
The OEIS is this incredible...
It's an incredible resource.
...online database.
Yeah.
With literally hundreds of thousands of integer sequences.
It's really remarkable.
And it's like this digital library where each sequence is kind of its own unique story just waiting to be told.
It's true. And what's really interesting is how these sequences connect.
Right.
Seemingly totally unrelated areas of math.
Absolutely.
And exploring these connections can really lead to some surprising discoveries.
Yeah, it's like this giant web of interconnected ideas.
It is.
And it's just fascinating to kind of pull on one thread and see where it leads you.
Absolutely. And today we're going to be pulling on a particularly interesting thread.
Okay.
We're looking at sequence A000001. Now, this sequence starts like this. 1, 2, 2, 0, 4, 2, 2, 0, 0, 0, 4.
That's a mouthful.
It is a mouthful.
Yeah.
And at first glance, it looks kind of random.
It does.
Can you tell us what makes this sequence special?
Well, the sequence is what we call a multiplicative sequence.
Oh.
And what that means is that to figure out any number in the sequence, we need to look at its prime factorization.
Okay, so prime factorization.
Yeah.
Let's just break that down quickly for our listeners.
Sure.
Prime factorization basically means you're taking a number and breaking it down into its fundamental building blocks.
Right.
Which are the prime numbers.
Exact.
So, for example, the prime factorization of 12 would be 2 times 2 times 3.
Precisely.
Okay.
So in the case of A000001, the prime factors of a number determine its corresponding value in the sequence.
Okay, so how do we go from those prime factors to the actual sequence value?
So there are a few rules that kind of govern the sequence. Let's start with the simplest one. Any power of 2, like 2, 4, 8, 16, will always result in a 2 in the sequence.
Okay.
So that explains a lot of the 2s that we see early on.
Right, straightforward enough.
Yeah.
What about other numbers, though?
So the number 3 is a bit unique. By itself, it maps to a 2 in the sequence. But any higher power of 3, like 9, 27, 81, those all result in a 0.
Interesting.
Yeah. So the prime number 3 gets a little bit of special treatment.
It does.
Now, for prime numbers bigger than 3, things get a little bit more nuanced. The rule depends on the remainder you get when you divide that prime number by 3.
Okay.
So if the remainder is 1, the sequence value is a 2. But if the remainder is 2, the value is a 0.
Okay, so to recap then, powers of 2 always give us a 2 in the sequence.
Yes.
The number 3 by itself gives us a 2, but any higher power of 3 results in a 0.
That's right.
And for other prime numbers, it depends on the remainder after dividing by 3.
Precisely.
Okay, I think I'm following along.
Good.
Now let's test our understanding a little bit here.
Okay.
Let's take the number 12,
Right.
which we already know factors into 2 times 3.
Yes.
If we're following our rules.
I think we might expect 2 times 2 times 2, which would give us 8. However, if we actually look at the sequence, the value for 12 is 4.
That's interesting.
Why doesn't it follow the rules that we just discussed?
Well, there's one crucial rule that we haven't mentioned yet. If a number is divisible by 9, which is 3 times 3, the result is always a 0, regardless of any other calculations. And since 12 is divisible by 3, but not by 9, we get the value of 4.
That makes sense.
Yeah.
So that divisible by 9 rule kind of trumps all the other rules.
Exactly.
It's like a hidden override.
It is.
In the sequence's logic.
Kind of a special case.
Interesting. Okay, so we've unpacked a little bit here, these seemingly simple rules that generate A00000091.
Yes.
But I have a feeling that this is really just the tip of the iceberg here.
Oh, absolutely.
There's got to be more to the story, right?
There always is with the OEIS.
So what else is going on with A00000001? Well, what's really remarkable is that this sequence can be calculated not only through these rules, but also procedurally using code.
Okay.
In fact, the OEIS entry for A000091 even includes code snippets in Maple and Mathematica.
Intriguing.
Yeah.
Sounds like we're about to dive into some
a little bit of
computational territory.
Computational territory, yeah.
But before we do that, I think it's important for us to let all this sink in a little bit for our listeners.
Definitely.
We've covered a lot of ground already.
We have.
So yeah, take a moment, folks.
Take a moment.
I think it's worth kind of highlighting, why code snippets are even relevant. in the context of a mathematical sequence.
Yeah, I think that's a great point. And some of our listeners might be wondering why we would even need code to deal with something that seems, fairly straightforward on the surface.
Right, exactly. It's all about scalability.
Okay.
So the rules we've discussed, they work well for small numbers. But imagine trying to calculate the sequence value for, say, a 10-digit number.
Manually factoring that number into primes and then applying the rules would be incredibly tedious.
Right. It would be a very manual and time-consuming process.
Exactly.
So the code is really providing us
Yes.
with a more efficient way
Absolutely.
to handle these calculations.
Especially as the numbers get larger,
Right.
where manual calculations become impractical.
Okay, so let's talk about these code snippets a little bit. You mentioned Maple and Mathematica. Could you give us just a high-level overview of what these snippets are actually doing?
Sure. So both of these code snippets, they utilize some advanced mathematical tools. And these are called the Legendre and Jacobi symbols.
Okay, now I know those terms might sound a little intimidating to some of our listeners. Could you kind of demystify them for us a little bit?
Of course. So imagine you're trying to figure out if a certain prime number, let's say 17, leaves a remainder of 1 or 2 when divided by 3.
Right, and that's a crucial part
Right.
of the rules for A000009. That determines whether that prime number contributes a 2 or a 0
Exactly.
to the sequence value.
Now, the Legendre and Jacobi symbols are like mathematical shortcuts. That let us determine that remainder information very quickly and efficiently.
Right.
They're tools that mathematicians use to analyze the properties of prime numbers in relation to other numbers.
So instead of having to manually divide each prime factor by 3
Right.
and checking the remainder, the code can use these symbols
Exactly.
to get that information directly.
Yes, it's like having a specialized calculator that just instantly tells you the answer without you having to do the long division yourself.
I like it. It's a shortcut.
Yeah.
It's elegant.
It is.
Yeah.
And so these code snippets really kind of reveal this deeper layer of mathematical elegance and how this sequence can be calculated.
Yeah, and it's a great example, I think, of how computational methods can really complement our understanding of these more theoretical concepts.
Absolutely.
But let's zoom out a little bit here. We've explored the rules, we've delved into the code.
Yeah.
We've even touched upon these interesting Legendre and Jacobi symbols.
Yeah.
But where does A00000091 actually fit into the broader kind of mathematical landscape?
That's a great question. And that's where things get really exciting.
Okay.
Because while A000091 might seem like a very niche sequence, its properties actually hint at potential connections to some really fundamental areas of mathematics.
Okay. What kinds of areas are we talking about here?
So, for instance, its multiplicative nature suggests possible links to number theory.
Okay, number theory.
Which is a field that explores, the properties of integers.
So how might this sequence be relevant to something like number theory?
Well, number theory deals with concepts like divisibility, prime numbers, modular arithmetic, all things that we've encountered, while exploring A00000001.
Right.
So the sequence's behavior might shed light on things like the distribution of prime numbers or reveal patterns in how numbers behave when divided by specific values.
So studying this seemingly simple sequence could potentially offer insights into deeper number theoretical questions.
Precisely.
Yeah.
And the connections don't stop there. This sequence might also have implications for cryptography.
Cryptography.
Which is the science of secure communication.
Okay, now that's an unexpected twist.
Yeah.
How could a sequence like this relate to something as complex as cryptography?
Well, a lot of cryptographic algorithms rely heavily on number theory, particularly the properties of prime numbers.
Right.
And sequences with predictable patterns, like A00000091, can sometimes be analyzed for potential vulnerabilities or used to generate keys that are difficult to crack.
So by understanding the underlying structure of this sequence, we might be able to gain insights into the security of certain encryption methods.
It's definitely an area worth exploring.
Interesting.
And there's even a potential connection to signal processing.
Signal processing.
Which is a field that deals with analyzing and manipulating signals, like sound or images.
Okay, now I'm really intrigued. How could a sequence of numbers relate to something like signal processing?
So signal processing often involves transforming signals from one domain to another, and this is often done using mathematical techniques like the discrete Fourier transform.
Ah, the Fourier transform. I'm familiar with that one.
Yeah.
That's a way to decompose a signal
Yeah.
into its constituent frequencies.
Precisely.
Okay.
And sequences, especially those with periodic or repeating patterns, can play a role in those transformations.
I see.
So it's possible that A00000091 or variations of it could be used in some signal processing applications, although this is still, fairly speculative territory.
This is incredible. We started with this seemingly simple sequence, and now we're talking about connections to number theory, cryptography, and even signal processing.
It's amazing, right? And those are just a few possibilities. I mean, the beauty of the OEIS is that it often sparks these connections that we wouldn't have anticipated.
It's like this launch pad for mathematical exploration.
It is.
It leads us down these unexpected paths, and it reveals these hidden relationships between different areas of study.
It encourages us to look beyond the surface and see the interconnectedness of all these mathematical ideas.
This is really mind-blowing. But before we get too carried away, I think it's time to bring our listeners back into the conversation a little bit.
Excellent, Paul.
We've given you a lot to digest here.
We have.
But the exploration doesn't end here.
This is where it begins.
All right, so we've explored this fascinating world of OEIS sequence A00000091, uncovering its hidden rules, delving into the code that brings it to life, and even speculating about its potential connections to other areas of mathematics. But now it's your turn to kind of take the reins.
That's right. We've equipped you with the knowledge and the tools. Now it's time for you to become an OEIS explorer yourself.
So where does someone even begin?
The OEIS website is a great place to start. Each sequence has its own dedicated page with comments from other mathematicians, links to related sequences, and often references to academic papers where the sequence appears. So it's really a rabbit hole of mathematical discovery, just waiting to be explored.
It sounds like a treasure trove for anyone who loves digging into the intricacies of numbers and patterns.
It really is.
And for A00000091 specifically, do you have a particular challenge for our listeners?
I do. I would encourage you to really dive into those Maple and Mathematica code snippets that we discussed earlier. See if you can understand how they implement the sequence rules that we talked about. Break them down line by line, look up the functions that they use.
It's like taking apart a beautifully crafted machine to see how all the gears and cogs work together.
Exactly. And as you work through the code, you might even find ways to optimize it, to make it more efficient, or even adapt it to explore variations of the sequence. Who knows, you might even stumble upon a brand new sequence worthy of its own entry in the OEIS.
That would be quite a feat, to be able to contribute to this vast library of mathematical knowledge.
It really would be.
It's inspiring to think that anyone with curiosity and a bit of mathematical know-how can really participate in this global effort.
It's a testament to the power of collaboration and the open nature of mathematical exploration.
So, dear listener, we urge you to take what you've learned today and run with it. Dive into the OEIS website, play around with the code, and most importantly, ask your own questions. Let your curiosity be your guide as you explore this fascinating world of integer sequences.
Because ultimately, mathematics is about the joy of exploration and discovery. It's about those aha moments when you suddenly see a connection you hadn't noticed before.
Beautifully said. And on that note, we'll wrap up our deep dive into A000091. We hope this exploration has sparked your curiosity and inspired you to continue the journey.
We'll be back soon with another deep dive into a different corner of the OEIS, so stay tuned for more numerical adventures.
Until then, keep those mathematical minds engaged. And remember, there's always something new to discover in the world of numbers.